Last time we talked about Turing degrees, hyper-computations, kind of what if games. If you can compute certain functions, then what else could you do? And the answer is still not everything. Even if you can compute undecidable things, there are things that are still undecidable in the face of that, which makes them even more undecidable, or doubly or triply impossible, if you will. And it's a whole hierarchy of impossible things. Again, this was news to humanity, that such a thing is the case. And we talked about the Turing degrees and their hierarchy and so on. This is all still the work of Turing, among many other things that he did. Any questions about that? Just kind of reviewing in a minute or two what we did the last time. So in the Chomsky hierarchy, you got your simpler languages, the regular languages, the context-free languages, then the context-sensitive languages, the decidable languages. The Turing degrees are way out here. They're outside the decidable, and some of them go into the not recognizable even. We already showed that the language is not recognizable, and its complement is not recognizable too, because if some languages are recognizable, but their complement is not recognizable. So in terms of good books about all that, I recommend going to the source. Gödel himself wrote a book about formal axiomatic systems and the incompleteness theorem. And there's lots of books on Turing degrees and Gödel's work and Turing's work. There's a nice article on the class website. You can read that for extra credit by Katin. He also explored undecidability and unrecognizability and Turing degrees, and in a nice colloquial way presented in a Scientific American article about what is knowable, what is computable, and so on. He defines a number called omega that's not computable. Anyway, it's a fun read, just a few pages. If you want to know a little more about these topics, that's kind of a good starting place, where to start. So this brings us to Johnny von Neumann, one of the greatest mathematicians who ever lived, applied mathematicians at that. So he contributed to almost every field of mathematics there is, and also physics. And of course, he founded computer science along with Turing and Church and others. And he invented game theory. The entire field was founded by him. Game theory was designed to try to predict what an adversary would do in various situations. It makes it easy if it's a zero-sum game. Your gain, their loss, and vice versa. Mathematically, it turns out to be a little more tractable if that's the case, but it could be used in other scenarios. And it can be used in various settings, like certainly politics. It was designed originally to try to figure out what the Soviets would do, whether they'll try to attack the US with nuclear weapons and so on. And so this is kind of a mathematical way of trying to reason about these things. But it doesn't have to be a warlike scenario. It could be in economics. Economics is a ripe place to apply game theory, where you have an adversary. Your adversary, if you're a buyer, the adversary is the seller, and vice versa. He's trying to maximize their profit at the expense potentially of the other party. And economics tends to be a zero-sum game, actually. You know, every dollar you make, somebody is losing, is giving it to you, right? And vice versa. So, but it could also be used in relationships, in all sorts of scenarios, with job searches, right? If you do a job search, you want to use a lot of game theory to maximize your earning potential, your job offers, your salary, your options, and so on. Anyway, he also tries to re-axiomatize set theory to get rid of Russell's paradox. That's a tough one. That paradox is very endemic in axiomatic systems, and he only had partial success in that. He was a principal member of the Manhattan Project. He helped basically create the first atomic bomb concept, the fission device, and he helped design also the fusion device later on. Fusion turns out to be much harder than fission. Fission, you just have to slam together two pieces of uranium-238. But to create a fusion bomb, that is to take hydrogen atoms and fuse them into helium, like the sun does it, at the rate of 4 million tons per second of matter converted to energy through E is equal to mc squared. That's hard to do down here on the Earth. You need extreme temperatures, extreme pressures to do it, and it's just an amazing engineering problem to which him and Stanislaw Ulam and Edward Teller had some very elegant solutions, if you can call it that, bringing a piece of the sun to the Earth. In one sense, it's elegant, but if you use it in a war, it's horrific, as we saw in Hiroshima and Nagasaki. Those weren't even fusion devices. Those were the smaller, weaker fission devices, the ones we actually used during World War II. So he's a pioneer of modern computer science. He invented the concept of the stored program. Today, it sounds kind of obvious, like where would you keep your program other than inside your computer, right? But no, in the old days, the program was external to the computer. It was on punch tape or paper cards, with holes in them, and that was code. And if you wanted to run it, you'd have to feed all those cards or tape into the computer, run the program. The output will go out on tape as well, and then it was a very kludgy, strange, kind of archaic process by today's standards. Of course, at the time, it was a lot better than what people can do by pencil and paper, like human accountants. But still, he said, why not store the program inside the computer itself? And the computer can refer to itself to get the instructions from its own memory and then execute them on its own memory on other pieces of data that are also stored there, and potentially on the program itself, because program and data now are interchangeable and they sit in the same place side by side alongside each other. I know it sounds obvious now, but at the time it wasn't obvious at all that this will be useful or efficient or universal or ubiquitous or a good way to do things. And the Von Neumann architecture, so-called, is named after him, and so is the Von Neumann bottleneck. We'll talk a little bit more about that in a second. He helped build the first physical large computer, the EDVAC, one of the early computers in the mid-40s, mid-40s, I guess. And he invented the field of cellular automata, the notion of computation taking place in a plane or in 3D space, and each cell can interact with the immediate cells. And essentially, he produced a simple model of computation that was equivalent to a Turing machine, but it wasn't a Turing machine. It was a cellular automata-based computer. And Conway's game of life, which is depicted here via this glider gun, is a very special case of cellular automata, but he created the general area of cellular automata. Conway created a specific cellular automata, namely the game of life, that has only 2 or 3, 4 rules, and it happens to be universal also. It can compute any function that a Turing machine can compute, or an arbitrary piece of code can compute. He investigated the field of self-replication, and specifically mechanical self-replication, or logical self-replication. How can a piece of code replicate itself without resorting to reading its own source from disk or memory? And that's actually a very subtle problem. You can actually take an instance of this problem by writing a program that prints itself out. Right? How many have ever written a program that prints out its own source code? But not by going to a file and reading the file. That'll be trivial and wouldn't be insulting your intelligence by doing that. And also, it's not true for self-replication if it goes to a file and reads it. It has no input whatsoever. Not a file, not keyboard, nothing. You can't even read memory. But when it executes, it needs to print out its own original source code, character for character, blank for blank, tab for tab, with all the quotes, everything in the right places, so that the Unix diff command will not be able to tell the difference between the source code of the program and its own output. For extra credit, go ahead and do that. It's only a few lines of code. Which language do you want to use? Whichever you prefer. This is not a programming language issue. You can do this in any programming language that you want. But whatever you do, don't pick a programming language where the blank program is a valid compiling program and just say, okay, the blank program is self-printing because it's blank and it doesn't do anything, so I've solved the problem. No, you just trivialized the problem and walked away from it without solving it. That's what you've done. So don't do that. So do it in C, C++, Java, whatever. Question? You can. You can do it in most languages. I mean, I'm sure there's some language probably that somehow the syntax is so convoluted and the constraints on the grammar are so severe that maybe you can't do it in some language. But in most languages you can do it, and you should be able to do it. So it's an honest to goodness algorithm. It's not about the actual language or its syntax. And of course, there's other mechanisms that can do this too. Can you name other self-replicating mechanisms from real life? Yeah, you are. We are. We can all produce clones of ourselves, right? It's called, pregnancy and offsprings and children, and even on a cellular level, mitosis. is a form of self-replication. A cell replicates itself. A DNA molecule can do this. It's a very large molecule, but has a regular structure, and through various means of chemistry and biology and the way molecules and atoms interact and their various bonds and forces between them and so on, and polarities, that molecules can self-replicate. So here was trying to do mechanically or engineering-wise what nature has already solved for billions of years. Right? Nature has this self-assembly flavor to it. Right? Protons and neutrons assemble into nuclei, the nuclei and electrons assemble into atoms, and atoms self-assemble into molecules, and molecules self-assemble into larger molecules, which then self-assemble into organelles inside a cell, and finally into cells, and cells assemble and self-assemble and combine to form organs, and then organisms like us, and simple or complex, and it keeps going and going, right? The whole universe is various levels of self-assembly, even at the planetary system. Rocks self-assemble into planets. Interstellar gas collapses and coalesces and self-assembles into stars, and so on and so on. And solar systems self-assemble in large conglomerations into galaxies and as galactic clusters. The universe has this hierarchical structure to it at various levels, many different levels, and somewhere in the middle between the whole universe and atomic nuclei is us. And by middle I mean there's about 30 orders of magnitude, and we're at 15 orders of magnitude into. We're halfway through, exponentially speaking, in terms of numbers of orders of magnitude between the very large and the very small. And sure enough, we self-assemble as well. It's a very interesting problem to investigate. Anyway, as a sideline, he also invented merge sort. If you didn't know that, now you know. Merge sort is due to von Neumann, and he did a great many other things. You can spend a whole semester talking about his accomplishments and inventions and discoveries. And there's a picture from the Manhattan Project. We have Ulam and Stanislaw Ulam and Johnny von Neumann, and there's the young Richard Feynman sitting there in a white T-shirt. So he gets a lot of credit. He was very, very sharp. Renaissance man, dabbled in a lot of different fields. There's a famous saying about him that says, most mathematicians prove what they can, but von Neumann proves what he wants. That's how much in high esteem other famous and good mathematicians held von Neumann in. There's some books about von Neumann or by von Neumann about his work. He did a lot of work in pure mathematics, in measure theory, in geometry, and various aspects of engineering and physics and set theory. The list goes on and on. So there's a lot of legacies of von Neumann. We already mentioned he tried to get rid of Russell's paradox by re-axiomatizing set theory. He proved Gödel's second incompleteness theorem independently, but of course Gödel gets the credit for all of incompleteness and so on. He worked on Hilbert's sixth problem, which basically said axiomatize all of physics, and we did a lot of work on quantum mechanics using Hilbert's spaces, higher dimensional, infinite dimensional spaces with a convergent norm. He invented game theory and the concept of mutually assured destruction, which in game theory parlance is called the Nash equilibrium. How many saw A Beautiful Mind, John Nash's biography? So Nash further pioneered and developed game theory that von Neumann invented and laid down. And this notion of Nash equilibrium, a mutually assured destruction in terms of nuclear war kind of world politics, it doesn't have to be a violent kind of or an aggressive kind of equilibrium. It's just a stable point that small variations or small perturbations of that point will not end up with arbitrarily large changes. And in the case of nuclear war, you want some sort of stable equilibrium that tiny perturbations to it pushes and shoves, and relatively small disagreements or arguments will not generate total global nuclear war and possibly the end of our species. Sometimes you see in a movie, some firefight, like in a John Woo movie, or two people with firearms kind of shooting all over the place. Of course, nobody dies because you got to extend it over many minutes, and it's in slow motion. And finally, the hero and the villain point the guns at each other and freeze, and neither one wants to pull the trigger, because if they do, the other will, in their death throw, pull the trigger too, and they'll both go out. So sometimes it's called a Mexican standoff. You might have heard that term. Mexican standoff is a Nash equilibrium, for example. They're kind of stuck, and nobody can make a move, and they're kind of locked into this situation. Basically, the U.S. and the Soviet Union for several decades were in this Mexican standoff, except instead of pistols, it was with nuclear weapons, and we sort of still are, actually. This is not over yet. So von Neumann kind of pioneered the whole scientific and mathematical study of these kind of situations, based on axioms and assumptions, and it's been proven very, very effective. A lot of economics are based on game theory these days. In fact, John Nash took it into the economics regime and won a Nobel Prize for his work on that. And there's many other things that are named after von Neumann and based after his work. By the way, the movie here with Peter Sellers, which movie is this? 1960s, Stanley Kubrick directed, Peter Sellers starred in 4 different roles. Dr. Strangelove, yeah. So that kind of harps on this mutual assured destruction aspect of the game theory of global politics of the 1960s. This global stalemate over nuclear weapons, and it started out actually as a serious film, as a thriller, but it was so ridiculous that it became a satire, and so Kubrick actually changed the mode into a satire in mid-filming, and it came out as almost a dark satire rather than a serious thriller. And there's a scene in there where the Russian and American generals are fighting with each other, punching each other, shoving each other around. The president says, "Gentlemen, no fighting in the war room." So that's one of the famous lines. Oxymorons, no fighting in the war room. Anyway, so that's a nice way to kind of get introduced to this concept, and it's both useful and frightening at the same time. That humans have to resort to this kind of mutually assured destruction to preserve the peace. It's ironic. Anyway, von Neumann languages and von Neumann architectures kind of correspond to one another. So these are language constructs, and these are hardware constructs, or devices or aspects of hardware. So the language and the architecture have parallel concepts. Variables correspond to storage elements in memory, or storage locations. Control in your language, like if then else, correspond to silicon test and set instructions. Back in those days, it was not silicon; it was vacuum tubes, and later became transistors and silicon. An assignment statement is a fetch and store into memory. And arithmetic expressions are basically memory references and ALU commands on the CPU, arithmetic logic units, kind of arithmetic. So the language kind of tracks the architecture, and that's both good and bad. It's good because it's efficient. If you know what the architecture looks like and it looks like this, then you might as well have these corresponding commands in the programming language that takes advantage of this particular architectural elements and capabilities. On the other hand, it's not so good because it ties you to the architecture. It makes the program very architecture dependent. And if you want to program something massively parallel, this begins to fail. And if you want to program something in a different way of programming, like functional programming, not procedural programming, again, this fails terribly. In fact, in functional programming, in pure functional programming, like pure Lisp, there are no variables, actually. How many have had functional programming experience, Lisp or Haskell, ASP? Yeah, it's a very interesting way to program, but this hobbles you if you want to go in these different directions. So he gets credit for pioneering a really good, nice classical architecture that works reasonably well, but then he gets blamed, as the von Neumann bottleneck phrase suggests, for the shortcomings of this architecture as well. So it's kind of a mixed honor to have both the architecture and its bottleneck named after you. But what is the von Neumann bottleneck specifically? So we have a CPU and memory, and it's kind of a fetch and execute cycle here between the CPU and the memory. And every time the CPU wants an instruction, it goes to memory, fetches it, then executes it, then puts the results back in memory. But the problem is this: CPUs have gotten faster and faster and faster over the years. It's gotten worse. Memories have gotten faster but slower than CPUs got faster. So now there's a huge discrepancy between the speed of a CPU and the speed of memory. How much faster is a CPU than a memory, modern CPU than a modern memory? What would you guess? The order of magnitude. I don't want an exact answer necessarily, but it's not that bad. Well, let's think about it. So CPUs run at how many megahertz typically? I mean, you see it on sales posters at Best Buy, right? Yeah, 3 gigahertz, roughly 3 billion operations per second, maybe 4 if you're really lucky and get a really fast CPU. How fast is memory, like DRAM or DD? Roughly again. Yeah, it's about half a gigahertz to 1 gigahertz. If it's 1600 megahertz, you can't really sustain that speed very long. So that's kind of a bit of a misnomer if they advertise it that fast. So anyway, it's about 5 to 10 times slower, even the really, really fast memories. So by the time you fetch one instruction from memory, the CPU can do 10 things. So mostly the CPU is sitting there idle. So it doesn't matter how fast it is, how much more faster it is. So if somebody's trying to sell you a 20 gigahertz machine, first of all, you can't really do this for other reasons. But if they said, I got a 20 gigahertz machine for you, you may be suspicious. And even if it's true that the CPU runs at 20 gigahertz, if memory is not much faster than it's now, a much faster CPU is not going to do you any good. Right? It's like saying, okay, I'm going to create a supersonic car. And I'm going to, how am I going to do that? I'm going to take a rocket engine, like from a spacecraft, and just strap it to the top of the car and just ignite it, and yeah, the car will go Mach 2. What's wrong with that scenario? I mean, a rocket can make a missile go Mach 2, Mach 3, Mach 4, so why can't it make a car go Mach 2, twice the speed of sound? Safety. What kind of safety? I mean, let's say you won't get a speeding ticket. That's not the issue.
You actually, when it gets, when you go for higher megahertz or gigahertz, the heat generator is more.
But I'm talking about a car and a rocket engine now, right? Are we talking about the same thing? Aerodynamics. Like, what about the aerodynamics?
Your tires can handle it?
Yeah, your tires. The wheels, the tires will be spinning so fast, the rubber will rip off the rims of the tires, for one thing. That's one bad thing that will happen. There's 2,000 other bad things that will happen too. The heating your windshield will melt the glass. The friction will be so high. The shock wave of the air, going underneath your chassis will lift you up into the air. You'll become airborne, except you don't have wings. You're a car. So it can happen, you can imagine what will happen the next 2 seconds after that. So you can't just take one aspect of a system and turbocharge it and say now the system is much faster and better than before. It doesn't work that way. So Intel is, for many decades have kind of bamboozled customers with this kind of, sales pitches that don't really make a whole lot of sense if you think about it. And you may have noticed it yourself. You get a computer that's supposed to be 3 times as fast as your old computer, but it doesn't feel 3 times as fast. You're lucky to get a 20% increase in the speed, not a factor of 3. Same thing with your iPhones. Your new smartphone is supposed to be 10 times as fast as the iPhones you had 3 years ago, but it's not really 10 times as fast. Maybe the CPU is 10 times as fast, but anyway, so this kind of bottleneck is not just the physical bottleneck, but it's also a logical bottleneck, an intellectual bottleneck, as John Backus famously said in his own 1977 Turing Award lecture, because it forces you to think in a von Neumann kind of architectural way. Fetch and store, fetch, execute, store kind of cycle. And so there's the bottleneck, that's a classical von Neumann bottleneck. And there's the bottle. So the 2 ends represent the difference in capacity or speed. But that's not the only bottleneck in a computer system. There's many other bottlenecks. Usually they talk about this one, but there's another bottleneck between memory and disk. So another bottleneck right there. How bad is this bottleneck in terms of the ratio of the speed of memory to the speed of disk? It's worse. How much worse? Yeah, in many instances, it's faster to download off the internet than go to your disk, actually. But how much faster is memory than a typical disk on your laptop, on your PC, on your typical computer? Just let's put a number to it, roughly.
So there's infinite bandwidth on the disk, because usually you can only do finite number of accesses.
Well, but how much slower are these accesses than accesses to memory is what I'm getting at. 3 orders of magnitude, 1,000 times slower? Do you guys agree, disagree? Is it too high, too low? Factor of 1,000? It's too low. Yeah, it is too low, actually. I mean, it's not wrong. It's at least 1,000. But what is it? So we already said memory can run at like, half a gigahertz or gigahertz speed, right? They're really fast memories. What's the seek time on a disk? Megahertz? You can seek millions of things on the disks per second? Does that sound right? How does the disk work? There's a rotating platter, and there's a read-write head that kind of moves around on a stepper motor, right? I mean, how many realize this? How fast can you move physically a piece of metal that, it's about a couple inches long? Can you move it millions of times per second with high accuracy? That doesn't make sense, right?
It's fixed. It's the disk is spinning.
The disk is spinning,
Right.
but if the head didn't move, you'd be over the same track all the time.
Oh yeah, it's moving that way.
So it's got to be moving. Whether it's moving sideways or back and forth, it's still moving. And a physical device is not going to move millions of times per second. Ain't going to happen. There's something called inertia that matter has, right? How many times per second can you move, roughly? And remember, you can't just move. You need to move accurately and position yourself along a specific track, and that track is smaller than a virus. They're really cramped together, really tight. Yeah.
Around 100 to 200 rotations per second.
So how fast does this spin? How many RPM? 7,200, yeah. Rounds, revolutions per minute. So per second, it's about 100 to 200 revolutions per second. But the physical read-write arm can move. What's the seek time? Typical seek time when you buy a hard drive. What do they advertise it as? Western Digital or Seagate, whoever makes those hard drives. I mean, you guys are computer scientists, right? Don't you know how fast your drives are? What's that? You use SSD? Okay, then you tell me how fast these SSDs. But most computers don't use SSDs yet. They use hard drives. They're slowly switching to SSDs, solid state drive, right? But even solid state drive is not that fast. It's faster than a hard drive, but not as fast as RAM. Right? But back to hard drives. What's the seek time on a hard drive? Let me back up. Why should you need to know that? Let me ask you that meta question. Why am I asking you that? Why am I expecting you as computer scientists, computer programmers, to know the seek time on a hard drive? Why does it matter? To you as hackers, as programmers, as developers. Does it not matter at all?
So that you will know when to trade off your...
Yeah, you need to know what trade-offs you're making when you're programming. Right? When you're storing stuff on disk and fetching it and storing it to disk, and you need to know how fast the disk is compared to memory so you know where you'd prefer to put the data and what the trade-offs are when you program. How many get that? I'm not making stuff up. I'm not just expecting you to know arbitrary things. If you don't know how fast the disk is compared to memory, you're not that good of a programmer. Sorry to break it to you. You're kind of limping along, crossing your fingers, hoping for the best. That's not a great strategy for excellence or high efficiency, hoping for the best, crossing your fingers. You need to really wrap your mind around these parameters of your system as you program it and try to make it efficient. Trade off, memory versus speed and capacity versus, fault tolerance and whatever. So again, the seek time on a disk is what, roughly, these days? Hasn't changed in years. About 10 milliseconds. How many times per second is that? Not a trick question. 100, yeah. I mean, millisecond is 1,000. Millimeter is 1,000 of a meter, right? So 100 times a second is you can fetch stuff from disk. You can seek on the disk. That's a lot for a physical, mechanical motion of actual maps that has inertia. 100 times per second. So this can fetch things 100 times a second. This can fetch things 100 million times a second or 500 million times a second. So what's the ratio of speed between the two? At least. How many orders of magnitude? At least 6, maybe 7, 6.5, 7. That's huge. That means this is 1 million times faster than that. So if you have large files you want to sort, don't leave them on the disk if you can help it, especially if the sorting algorithm goes to disk and fetches a lot of things and swaps things, and that'll really cripple you really slow down your sorting algorithm, whatever algorithm you're running. And of course, there's more bottlenecks besides that between disk and the internet. Disk is not as fast as memory, but it's usually faster than fetching things from a remote server, except in a few cases it might be the other way around. But generally, you get another bottleneck there, and there's other bottlenecks up and down the hierarchy that I'm not showing you. So there's a factor of 10 here, a factor of 1,000,000 here, and several order of magnitudes there typically. On a good day, there might only be one order of magnitude there between disk and the internet. Okay, any questions about any of that? So again, the takeaway message is not so much the actual numbers, but the fact that they're dramatically different, and you need to know that as you program and develop stuff and engineer applications and so on. You can't just ignore these things, otherwise you won't be very effective, or what you produce won't be very, very impressive. You'll just kind of limp along, but not really fly. So functional programming try to get rid of the intellectual bottleneck, never mind the physical bottlenecks, on how we think about computations and programming, and the marriage between hardware and software and their correspondence and so on. And languages like Haskell and Lisp and ML and Miranda have tried to address this intellectual bottleneck and kind of think about programming in a different scenario, and with various levels of success. There's probably places where functional programming is really good for, and others which is not so much. Right. So there's von Neumann, and who is this other guy? Anybody recognize him? They're next to the EDVAC, one of the very early computers, electronic computers. Give you a hint, it's in the Manhattan Project, where they invented the atomic bomb the first time. Dr. Strangelove? Well, that's Peter Sellers in the movie, but this is not a movie. This is real life here. Or Ellie? Yeah. Yeah, it's Robert Oppenheimer. He was a director of the Manhattan Project. So the EDVAC, just to calibrate this for you, had 1,024 words. That wasn't the size of a word. That's the number of words the computer had. 44 bits each. So it's about 5K, 5 kilobyte. Today in 5 kilobytes you can barely store a page of text. But that's the entire memory of the machine. Of course, it was big vacuum tubes, a room full of vacuum tubes. The cycle time was roughly 1 kilohertz, not 1 megahertz, not 1 gigahertz, 1 kilohertz, about 1,000 operations per second. It can multiply about 300 times per second, multiply pairs of numbers. Of course, a computer nowadays can multiply hundreds of millions of times a second, maybe over 1 billion times a second. Magnetic tape, no disks, thousands of vacuum tubes, required 56 kilowatts. 56 kilowatts is probably more than this entire building takes, actually. Weighs almost 8 tons, took 30 people to operate. Just again, to put it in perspective. So there's people operating it, and of course today, an iPhone looks and operates much faster than this entire computer. I drew in here a big iPhone. The iPhone, of course, sits in your pockets, and that's one of the original manuscripts by von Neumann himself, explaining how this contraption works and what it can do and how to program it. There are some studies on self-replication and self-reproducing automata by von Neumann, and he tries to mimic the things that biology do, that DNA does. And he succeeded in designing general self-replicating mechanisms. For the first time, he mathematically and engineering-wise proved that we can do this mechanically, what nature has already been doing for billions of years. By the way, one of the incentives for self-replication, for mechanical or computer self-replication, was space exploration. If you send a spacecraft to the stars, they figured humans aren't going to be going there anytime soon, but we'll have robots and computers going there, and machines tend to fail and degrade and have to be replaced. And so if you send machines out there to explore the planets of other solar systems, even the fastest rockets we have today will take about 100,000 years to reach the closest star. closest star is Alpha Proxima. It's 4 light years away, roughly. And we already sent spacecraft past the edge of our own solar system, past the orbit of Pluto, Neptune and Pluto, and that took about 40 years for them to get there. They were launched in the 70s, and they finally just made it there, and now they're exiting the solar system. But the nearest star is 4.5 light years away. Pluto is only 1 light day away. Light takes a day to get from the sun to Pluto. Light takes about 8.5 minutes to get from the sun to right here. So this planet here, right here, is 8.5 light minutes away. Pluto is 1 light day away. Mars is about half a light hour away. Nearest star, 4.5 light years. So you need machines that can replicate themselves and also repair themselves if they're going to last 100,000 years in these journeys. And maybe terraform star systems and then wait for humans to kind of follow in their heels one day, maybe. So that's one of the reasons they were thinking about self-replication automata, self-reproducing and self-replicating and self-correcting automata. And you can do this in software. You can do this in hardware. It's harder. Software is a little easier. And patents have been issued about self-replication, self-replicating mechanisms, and so on. And it's still a growing field. And of course, factories today are based on these ideas. So you have car factories are almost completely mechanized. You know, computer factories, many types of factories have robots building other machines. And in fact, where do these robot arms come from? There's a robot arm factory somewhere, and in this robot arm factory, you have robot arms building other robot arms, right? That's also an assembly line. That's mostly computerized and automated. So you have robots building other robots. We have that already. It's not fully general, but it's getting there. One of the earliest factories that we have machines build other machines is the Apple Macintosh factory back in 1984. How many have heard of that innovation? So it's one of Steve Jobs' innovations out of hundreds of other innovations that he did, including the iPhone, the iPad, the iPod, Pixar. He did a lot of stuff, but he created a factory that's almost fully automated. It's machines building other machines. And of course, in the movies, we see machines build other machines, and when it gets general enough, you got Terminator-type movies where machines self-replicate. This is a takeoff on the Escher sketching hand-drawing hand, except they're both cybernetic hands. There's a nice article on the class website, again, Scientific American article, that very colloquially, nicely explains self-replication and the issues about self-replication, and gives you some simple examples of self-replication. Talks about, of course, RNA and DNA, but also mechanical self-replication. You can even do it on a chessboard. You can have a configuration on a chessboard with a few simple rules that if you apply these simple rules here, this configuration will self-replicate into 2 copies of itself side by side on a chessboard. So, this is kind of a logical self-replication. You still have to move these pieces and lay them down, but it's a very simple set of rules that result in self-replication. And if you apply these rules again to these configurations, you'll have yet more copies. So that's just an example of a replicator in terms of pieces on a chessboard. But there's many types in different scenarios, and robots that do this. Of course, the problem of writing a piece of software that does this, I actually mentioned on that slide. We kind of glossed over it, but I mentioned that earlier. Write a program that prints out its own source code. Try this. This will be both the shortest program you ever wrote and also probably the hardest. So it's an interesting exercise. You can do this in 1 line in C. When I say 1 line, I mean less than 100 characters, less than a tweet. But it ain't going to be easy. It will be the hardest line you ever wrote, because it usually takes just a few seconds to write a single line of code. Right? This one might take hours. So please try this. And again, don't cheat. Don't go to a file and read it from there. That's not the exercise. All right. Don't go to memory and see where the file has been stored by the compiler or whatever. That's not the exercise either. The program has to have truly no input and just print out its source code exactly. It's also interesting how this problem is specified. Usually, when you specify a program, when I give you a programming exercise, anybody gives you a programming exercise, they say, here's what the input is and here's what the output should be. They give you two things, input specification and output specification. That's how you usually get a program specified to you, whether you're a programmer in a company or a student in a class. This problem is not specified as an input and an output. It's specified in a convoluted way in terms of itself. The program needs to print out whatever that program is. It's a very different way to specify a program. There's no input and output pair specification. Okay. So anyway, I really urge you to try that. If you think it's easy or unimportant or not worth trying, your mind isn't wrapped very tightly around self-replication and all of its ramifications. It's very subtle. Okay, so that too we owe by Neumann, self-replication. And there's an institute about his work. Even to this day, we still track the implications of his work. There's yearly conferences. There's a von Neumann Theory Prize, and he gets a lot of street cred for all the stuff that he's done. There's a von Neumann Computer Society, and they meet regularly. Okay, any questions about von Neumann? Very prolific guy. So Claude Shannon, again, a contemporary of Turing and von Neumann back in the 30s and 40s. He invented electrical digital circuits. He didn't invent electrical circuits. He invented electrical digital circuits. The notion that the circuit has two states, on or off. Before that, there were plenty of computers that were analog computers with continuous varying quantities. You can have voltages of various arbitrary continuous levels, or currents of various levels, resistances or capacitances of various levels, and you compute using analog, devices. But he said, let's make it digital. Let's make every circuit has an on and an off state, and that's it. Nothing in between. Of course, when they switch, it goes metastable a little bit, but then very quickly settles on one or the other. So basically, he took what Boole did and implemented it in circuitry, right? And he also introduced the term bit. Bit is due to him, binary digit, bit. And he contributed to genetics, cryptography, and many other studies. He was in the Institute for Advanced Study again, along with all these other luminaries, Einstein, Gödel, Shannon, Turing, Church, Feynman. All these people were there, influencing each other, rubbing shoulders on a daily basis. And he invented information theory. And information theory is a study of information, the transmission, the generation, the entropy of information. He invented the notion of entropy for information. Entropy was known as a statistical dynamics, a physics quantity, a disorder in a physical system. But he adapted it to bits and bytes, to information. We'll talk a little bit more about that in a second. And many things are named after him, like the Shannon source coding theorem, the Shannon limit, Shannon decompositions. And he had a bunch of cool hobbies like juggling, unicycling. He invented some of the earliest computer chess playing automata. Right? Back in the day, there were no general computers. He invented specific computers to play chess and play it reasonably well. So he was really a tinkerer, and AT&T Shannon Labs are named after him. So there he is in various contexts, both young and old, and he was just very brilliant. All of our devices today are based on his work. Every time you pick up a phone and make a call or tweet something or download a web page, you're using his inventions about information theory, channel capacity, encryption, compression, entropy limits. So his master's thesis in 1936, I guess it's in 1940, his bachelor's from 1936. So his master's thesis in 1940 basically laid down the foundation for switching circuits, for digital circuits. And again, today, all our computers, our smartphones, all of our devices are based on his ideas for switching circuits, namely, binary circuits, circuits with Boolean circuits, circuits with only two states, mostly. He also invented maze running devices that actually learn from their mistakes and improve as they go. So that's one of the first learning machines. It was an AI experiment. AI has come a long way. Nowadays it can do all sorts of cool things. But back then, to have a machine learn as it goes was very, very novel. To do more than it was programmed to do originally. To kind of learn from its mistakes and from its experiences. World champion, chess champion Ed Lasker helped him, build one of the first chess-playing engines at the time. This was late 40s, early 50s. And here's pictures of his study at his home. He just died relatively recently at a very advanced age. But in his study, he has a poster on his wall. Can anybody recognize this guy in the poster? It's a little fuzzy, but it's David Hilbert. Yeah, remember we talked about Hilbert quite a bit last time, in his famous 23 open problems. So here's yet one more influence of Hilbert. He influenced Shannon to pursue a lot of these studies, and Shannon, not surprisingly, paid a lot of homage to Hilbert and had, in fact, a poster of him on his study wall. He was also an avid juggler. He was a really good juggler, too, as a sideline. He created this on-off machine that when you press the button, when you pull this button, the machine would turn on, and the electrical engine would have this mechanical arm go out of the box and press the button off and go back into the box. So it was called the on-off machine because when you turned it on, all it did was turn itself off. So it was kind of a gag, but it was a pretty clever, hard to design kind of gag. And his information theory was published in one big paper in 1949. It was probably 100 pages. One of the best, most influential papers ever written. Others being Einstein's theory of relativity, Turing's paper from 1936 with the undecidability, Gödel's paper of incompleteness, and a few others. His is definitely in the top 10, probably in the top 5 for sure, because all of our communications devices and computing devices and smartphones are all based right on this paper right here, 1949, where he invented in one fell swoop the theory of information theory. So I'm going to show you a few pages from his paper, which is really a small booklet. And he talks about the effects of noise in a channel, right? The fundamental problem of communication, he says, is that reproducing at one point either exactly or approximately a message selected at another point, right? And hopefully the messages have some meaning, so it's used for communication. You can select it from a possible set of messages. And there he is inventing the word bit right there in this paragraph, right? So a bit was basically a single binary digit, yes or no, or on or off, if you talk about circuits. And he talked about the circuit capabilities and the channel capacity given as this formula right here. And this is a theoretical channel capacity, but you can actually reach arbitrarily close to the theoretical channel capacity. And in fact, our devices do that today. They operate at very close to the theoretical limits of whatever medium they're communicating on, whether it's a twisted copper pair, fiber optic, or coax cable, or category 5 ether connection, or whatever. He showed how to reach arbitrarily close to the actual theoretical capacity of the channel. And so that's a classical diagram that he used to show an information source and an information destination, and there's a transmitter and the receiver, right? And then you select the message and transmit it. Here it's received, gets decoded, and then sent to the destination. And this channel could be arbitrarily long, right? This channel could be just a few centimeters inside, or it could be across your computer a couple of feet, or it could be across a room, or across a building, fiber optic across a building, or it could be across a state or a country or a continent, thousands of miles of fiber, or it can be from here to outer space somewhere. These are all just channels of communication. And he introduced the noise source on the channel. Again, the noise source could be arbitrary. It could be very high noise, it could be white noise, it could be other kinds of noises, it could be an adversarial kind of a noise designed to fool you or trap you into disclosing things you shouldn't. And this diagram gets a lot of mileage. You can see it many other places. But it appeared originally in his treatise on information theory, and he analyzes the channel capacity versus the noise source, and how to encode things and even avoid errors, do error correction and even do compression, if you will. And he defined entropy as a formula that's basically the sum of products of probabilities and logs of these probabilities. And the entropy is maximized when the probability is 50-50. If you don't know anything about the bit, it could be either 1 or 0. And it's 50-50 chance. That's when the information has the highest value. Each bit carries really 1 unit of information. But if you can predict the bit with very high certainty, if most bits are 0 and very few are 1s, that has very low entropy and low information content, correspondingly to this kind of parabolic curve. So this kind of formula was known already in statistical mechanics, but now he adapted it to information flow, and that was just a brilliant move. It didn't occur to anybody before to do that. There's a correspondence between information content and thermodynamics, basically. That was, one is not like the other. Thermodynamics is like kinetic energy across molecules and collisions and temperature, right? Information content is how much information is contained in a sequence of bits. One doesn't even feel or sound like the other, but they're very, very intertwined. And he had this observation and this insight. In fact, today, when especially in the studies of black holes and event horizons and singularities, information theory comes in very, very aggressively into the physics studies of extreme gravitational situations like black holes, where matter collapses on itself. Stephen Hawking, has pioneered those kind of connections between black holes and Shannon's information theory, and there's something called the holographic principle. How many heard about any of this? Am I sounding crazy? Okay, good. So a few of you, I'll take that. And so there's very, very deep connections between these subjects and fields and concepts, and he even called it entropy. It didn't have to, but he did, and for very good reasons. So he talked about noiseless channels and channel capacity, and he showed that you can approach the channel capacity to arbitrarily epsilon distance away from what it can do. A little bit more about entropy. It measures the uncertainty or surprise you see in a system, how randomized it is. And if a system is very ordered, the entropy is very low, right? And you can prove that most strings are random. Arbitrary strings in sigma star are random strings. You can prove that most of them are not compressible even by a single bit. In fact, have we proved that already? No? Okay, let's prove it right now. Prove right now that most strings in sigma star are random strings. And by random string, I mean strings that cannot be compressed. If a string is compressible, it's not random. Let me give you an example of a very long string that has a very short compression. A Google zeros. There. I'm done describing it. A Google zeros. And you know exactly what string I'm talking about. It's 0, 0, 0, 0 a Google times, 10 to the 100 times. So it's a very, very long string, but has a very, very short description. That means it's highly compressible, which means it has very low entropy, which means it has very little information, this string. Let me give you a string that's not so compressible. Shakespeare's Hamlet. You may get a little bit of compression, but you won't get a Google to 1 compression like we did in the other one. Right? So Shakespeare's Hamlet contains a lot more information than a Google zeros. So how would you, and both of these are strings in sigma star. Google zeros is one string, Shakespeare's Hamlet is another string, assuming sigma is the English alphabet with all the digits in there too. So how would you prove right now that most strings are not compressible? Most strings are random. By most, I mean more than half.
How do we define compressible? Is it finitely describable?
A compression has to be shorter than the string, and the string should be completely, uniquely reconstructible from the compression. In other words, it can't be a lossy compression. It has to be a lossless compression.
And the compression can also be infinite.
What do you mean by infinite? The string is finite. The string has k characters in it. The compression hopefully has less than k characters in it, because if you use more than k characters to describe k characters, you might as well just use the k characters to describe the k characters and forget the compression. Compression is just the string itself. It's the trivial compression. I mean, it's still a compression, but it's the null compression. It's a trivial compression that doesn't do anything. It's f of n is equal to n. It's the identity function compression. It's also easy to uncompress that function, just leave it alone. Right? So to compress, you really need to reduce the description of the string by at least some amount. Theoretically, by at least 1 bit or more. Hopefully, more than 1 bit. Factor of 20% or 50% or factor of 10 or 100 or a billion. Now, some strings are more compressible than others. Right? If I say, the string containing a billion 0-1 alternations, 0, 1, 0, 0, 1, 0, 1, a billion times. What's a very short compression of that? 0, 1 times 1 billion, so that's 9 more characters. End of story. Repeat it. Or 0, 1, you can write it down as 0, 1, to the billion. Okay, so you have 10 characters here, 4 more characters. So in 14 characters, I describe that string. If you want the exponent to be described also as a character, like a caret, okay, 15 characters, I describe a string of size 1 billion. Actually, it's of size 2 billion, because 0, 1 is 2 characters times 1 billion is 2 billion. So the compression is 1 billion is 2 billion divided by 15, right? Which is roughly, 150 million time compression. I compress by a factor of 150 million times. How many see that? Yeah. Okay. Here's what I'm trying to get you to prove. Most strings are not compressible at all by even a single bit. That's a very bold statement, by the way. How would you prove that? Tell you what. Prove it in 2 words. Yes, you heard me right. I'm not crazy. 2 words as the basic idea of the proof. That will force you to focus on the most important aspect of the argument, because you only got 2 words. And once you use 2 words, then prove it again using a sentence or 2. It's always a good exercise to nail something down in just 1 or 2 words. It really forces you to see through all the flash, the flack and the noise and the non-consequential issues, and focus on the bare bones truth and insight. Look for the gem. All right, so what 2 words would you want to use? How many have some inkling of the argument? Well, good. So how come I don't see more hands? All right. Irrational numbers? Okay. Any thoughts about that, or other pair of 2 words? I appreciate you speaking up. People seem to be afraid to say anything. The only one talking here. Well, me and you. So that's good. I appreciate that. Yeah. By contradiction. Okay. I can see how that could be descriptive. What else? What other 2 words would you use? Pigeonhole. Is that 1 word or 2 words? Pigeonhole or pigeonhole? Well, if it's 1 word, you cut it down from 2 words to 1. That's even better. That's a 50% savings right there. It's a good compression, 50%. Okay. How many see pigeonhole somewhere here? Pigeonhole principle. Okay. You want to now expand that word or 2 into a sentence or 2, describing what they mean by pigeonhole? Anybody? Besides the person who said it? Presumably he understands what.
We can assign the string an integer.
Okay. Okay, it's a good start. Assign strings integers. By the way, what's that called? That technique? Dovetail. Yeah, it's not diagonalization. It's dovetail. Okay, what else? Where is this going? So pigeonhole principle, so let's go with that. So that's a hint now. You got to losslessly compress a string. Lossless compression means the original string should be uniquely reconstructible from the compressed version So two different strings cannot have the same compression. How many get that? Otherwise, it's not lossless. Because two different strings, two unique different strings, not equal to each other, have the same compression. You don't know which one to uncompress that compressed version into. Right? It's ambiguous. So it's got to be one-to-one mapping. It can't collide in the range, right? The compression function. You can take two things in a domain, compress them into the same compressed version in the range of that compression function. So what else can you say at this point? Yeah.
There are fewer strings shorter than a fixed length than there are strings of that fixed length.
Yeah. So if the compression function can collide in the range, the number of compressed strings, the number of compressions that are smaller than any given string of fixed size k, the number of strings smaller than k that can be construed as compressions is less than the number of strings of size k. Let's say the alphabet is binary, so it says 0, 1. So how many strings are there in of size k on a 0, 1 binary alphabet? Not a hard question. Trivial question. 2 to the k. Now, if the compression is smaller by at least 1 bit and is of size k minus 1, how many of those compressions are there of size k minus 1 that are binary charactered string? 2 to the k minus 1. How much smaller is 2 to the k minus 1 than 2 to the k? Factor of 2. So if all 2 to the k strings were compressible, there's only 2 to the k minus 1 possible compressions, assuming that it's compressible by even 1 bit, never mind much smaller. Which means what? There's a lot less compressions than there are strings. And it's got to be unique. No two strings can compress into the same compressed version. Otherwise, you won't be able to uniquely uncompress. And it's got to be losslessly. So it's a lossless compression, so it's got to be losslessly uncompressible. So there's only half as many, roughly, compressions as there are strings. So most strings are not compressible. There aren't enough compressions to go around. There aren't enough shorter descriptions than there are strings. So some of them will not have shorter descriptions, no matter how clever the compression scheme is. It's not about the cleverness of the compression here. It's a counting argument. It's pigeonhole principle. Too many pigeons, not enough holes. So some pigeons will collide in a hole, which cannot happen, because it's got to be uniquely compressible. So how many understand this argument? Which means most strings are random. We just proved that most strings are random. Is everybody good with that proof? It's a formal proof. Yeah.
Would you say that it's the sum of from k equals 0 to k minus 1 to
Sure. Yeah. So.
less than
Yeah. Yeah. So what he's saying is that the compression doesn't have to be 1 bit less. It could be several bits less, or even many bits less, and you got to count up all the smaller compressions as well as the large compression. So, but you will end up, if you count all of those, less than the original number. Okay. Yeah.
So if you toss the coin n times, you get a string, and those are uniformly distributed, all the possibilities. Like you get a uniform distribution of all the results. How, like one of the possibility you get all zeros, and the other is probably it look random to human beings, but in a probability system they're equally random.
Yeah. So right now we're not talking about probabilities. We're talking about deterministic compressions. Right?
That randomness is defined by.
Yeah, so we operationally now define randomness as incompressibility. In other words, if it was random, if it was truly random, there's no way to compress it into something smaller than the actual set of bits that were the random bits. And conversely, if it was compressible, it's not random, because there's some pattern in it that we can describe more succinctly. Like this extreme example here, where the pattern was so trivial, 0, 1, 0, 1, 0, 1, 0, 1, a billion times, that we can compress it by factors of hundreds of millions. Most situations are somewhere in between. There's extreme compression and no compression at all. So yeah, some strings are highly compressible, like that one there. But at least half of them are not compressible at all, whatsoever, even by a single bit, amazingly enough. Which is almost counterintuitive, because you think random strings are rare. Most strings have some pattern. Even Shakespeare's Hamlet is compressible. You take one of the words, I don't know, one of the most commonly occurring words in there, and assign to it some smaller word, and then do the substitution, and now you've compressed it by a good number of a few thousand bytes or something. Most texts, most files, most pieces of code, most images are compressible. Those aren't the random ones. So it's kind of a weird situation. Here's something even weirder. The problem of determining whether a given string that I give you is random or not random, compressible or not compressible, how hard is this problem? Would you guess? Take a wild guess. It's undecidable. So even though most strings are random, detecting even one of them as random correctly is undecidable. Which is, again, a weird, it's not a contradiction, it's just counterintuitive. It's not only undecidable, it's unrecognizable too. The problem of determining whether a string is random or not is not only not decidable, it's worse than that, it's not even recognizable. You don't even know it when you see it. And you certainly don't know it when it's not random. Question?
That like it seems like that would depend completely on your compression scheme. So you could have, let's say, like some compression compresses a string with like 1, and then that string is compressible. It's like any string is compressible if you define a compression algorithm to compress that string.
Well, so you can say the digit 1 corresponds to Shakespeare's Hamlet, for example. So that's your code word for Shakespeare's Hamlet, just saying one bit. But if you do that, many other strings will not be compressible under that scheme. So this proof is resilient to the scheme, actually. Also, if you decide to do that, to make the dictionary like a dictionary compression, small words correspond to larger words, and you put them all in a dictionary, and say that's my compression scheme, you have to consider the size of the dictionary now as part of your part of your compressed string. You can't do an end run around that. You can't just say I'm going to have the digits from 1 to 1,000,000 correspond to all the books ever published, or 100 million books. The integers from 1 to 100 million will correspond to all the 100 million books published throughout human history. There's about 100 million of them, maybe 150 million. It's hard to say because some books are long extinct and lost to time. But that's not a complete compression scheme without actually giving the dictionary of all the books and all their digits, all their numbers as part of the scheme. So you haven't compressed all the books in the world to just 1,000,000 integers in of itself. There's information missing there, namely the dictionary of the compression. And that will be the size of 100 million books, plus 100 million integers on top of that. So you can't kind of make an end run and cheat around the compression by shoveling the complexity of the compression scheme under the carpet and not expect to pay for that. I hope that makes sense. Yeah, question? Yeah.
So would you encode that dictionary into the Turing machine that actually does the decompression?
If a Turing machine is going to do this decompression, you'll need to encode that whole giant dictionary into the finite control. So it'll be a heck of a lot of states on that Turing machine. Or a heck of a lot of program lines if you try to hardwire all these books into strings in the program. It'll be a very large program. Okay, so we just proved that most strings are not compressible, and yet determining whether any given string is compressible or not is undecidable, and it's not even recognizable. So on the problem sets, I give you these two problems. Prove that most strings are not compressible. Prove that whether a string is compressible or not, i.e. random or not, is undecidable, and separately prove it's not even recognizable. And then I think if I'm not mistaken, there's yet another problem showing that the set of compressible strings has no infinite recognizable subset at all. Not only it's not recognizable to tell if a string is compressible or not, it has no infinite recognizable subset. So it's even worse. So there's some of the problems on the problem sets. They're not that hard to prove, actually. There's relatively short proofs to each of these. Okay. So entropy quantifies information content. You can think about maximum entropy of a bit is when the probability is 50-50, whether it's heads or tails or 0 or 1. So that's where probabilities do come in when we talk about the expected outcome or the expected value of a particular bit. And a biased coin has lower entropy than a fair coin. So if the coin is like 90-10 to come up, 90% heads but only 10% tails, it's heavily biased for whatever reason, then it has less entropy and less information content. And if it always comes out heads, the entropy is 0. So, because if you flip a coin, it's double-headed coin, it's always head, it'll never be tail. So to generate a bit with that coin, I flip it, it's heads. Flip it again, heads. Flip it again, heads. Well, no big surprise, it's got heads on both sides. So you might as well not flip it. You know it's going to be heads. Forget the coin. The coin bears no information whatsoever. It doesn't do you any good. So the information content is on this far end. Right? 0 probability of tail, 1 probability of head. So that's how it goes. Right? So we already mentioned that a long string that very, very easy to anticipate has 0 entropy, and English text has an entropy roughly of 0.6 to 1.5 bits per letter, roughly. Yeah. English doesn't have very high entropy compared to some other languages. So if I write down a word with some of the letters missing, just to show you that the information content of many letters in a word is almost 0. So if I say, if I write a word without, which word am I trying to write without the vowels here? Making, it's pretty clear, right? It's maybe there's a tiny bit of ambiguity, but not very much. So you can omit almost all vowels in English and not be worse off for it, most words, right? Sometimes when the media wants to convey a dirty word, but we're too puritanical to actually say it, we put a couple of stars in the middle, between the F and the K or whatever, between the S and the T. But you know which word it is, right? So why do we do that? Well, because we're very puritanical, not in a good way. But the point here is what? That the entropy of different letters in a word is very low. So low that you can omit them altogether and you still know what the word is. In other words, they're doing compression when they put these stars in words and stuff. Right? Think about it. So English has very very low entropy compared to other languages. Chinese has very high entropy, actually, because there's a lot of characters and they have very different meanings, and it can be interpreted in many different ways. In fact, there's a famous case of a Chinese dissident wrote a poem that was made of a block of 5 by 5 Chinese characters, 25 characters in a 5 by 5 matrix. And if you read it top to bottom, like you read Chinese normally, it exalted the Communist Party and said that the state is wonderful, and the Communist Party is amazing, and the chairman is doing a great job. And so they published it in a newspaper. If you read it sideways, it said the party is corrupt, and the premier is a criminal, and same characters. But it got past the censors. The only way you can do this kind of clever trick is if the language has very high entropy. Think about it.
So because back in the old days, we don't have paper, so you have to compress a lot of characters.
Yeah. So it's out of necessity, right?
Yeah, Asian Chinese, 1 character is 1 word.
Yeah.
But now because we have papers, now we have luxury to type out stuff on the phone or on the internet.
Yeah.
So the new vocabulary normally has more than 1 character. So you can see the entropy is growing as a result of technology.
The entropy is decreasing. Yeah, it's the other way around. Yeah, it's less compressed now. It's more fluffy, right? Yeah, that's a good point. In fact, when you do crossword puzzles, you want high entropy in the language to do crossword puzzles. If the language has low entropy, crossword puzzles don't work very well, if you think about it. And if the language is high entropy, crossword puzzles work a lot better. Anyway, I'll let you think about all these things. So, by the way, here's a famous problem that was coined by Neumann. Actually coined, no pun intended, because it's about a bias coin. If you have a coin with a bias in it, but the bias is fixed, and you know it's fixed, you don't know what the bias is. So the coin is not 50-50 heads or tails. It's K, it's P and 1 minus P, heads or tails. The probability for heads is fixed at P, and tails, of course, 1 minus P. But you don't know what P is. And from it, you want to simulate a fair coin with 50-50 unbiased outcome. How do you do it algorithmically? You can think about the coin as a subroutine that returns a 0 or a 1, but with P and minus P, P and 1 minus P probability, not 50-50. Actually, it still works if P was 50-50, 50%, 50%, P was 0.5. But in general, it's not 0.5. How do you construct a fair random binary digit subroutine from a biased binary digit subroutine, but with a fixed bias of P that you don't know what it is? I understand the question. Okay. How many have an answer? Okay. 3, 4 people. Have you heard this question before? The algorithms course. See, these problems come back to haunt you now with a vengeance, because now there's lots of other questions about entropy and bias and compressibility and randomness. Okay. So those who haven't heard it before, let's give somebody a chance who haven't heard it before. How would you solve it? Anyway, think about it. We'll come back to it in a little bit. But any questions about what the question states? You have a subroutine that returns 0 or 1 with P and 1 minus P probability. And from it, you want to build a subroutine that returns 1 or 0 with 50-50 probability. Okay. So we only mentioned information entropy is an analog of thermodynamic entropy in physics, in statistical mechanics. And the second law of thermodynamics says that the entropy of a system cannot decrease. It could increase, or if you're lucky, it could stay put. So when ice melts, actually is an example of entropy increasing. Disorder increases. Crystal is much more ordered than liquid. In fact, gas is even less ordered than liquid. So entropy is kind of the analog of disorder or chaos, and it's also connected to the error of time in ways which we not completely fully understand as a species. If you carry it enough, to an extreme, you get sort of heat death of the universe kind of arguments, and black holes, and thermodynamics, statistical mechanics, information content. They're all very connected, but we're still exploring all these connections. And Stephen Hawking is one of the guys that did that. He's just passed away, unfortunately. He lived quite a long life. But quantum computing uses quantum information theory to generalize classical information theory. So you can have a whole quantum information theory, and we do. And this we already mentioned. String compressibility decreases as entropy increases. We just mentioned this and proved it a few minutes ago. Most strings are not losslessly compressible. Pigeonhole principle, right? That's one way to prove it in 2 words, or 1 word, pigeonhole. And so most strings are random, and we already mentioned it's not decidable or recognizable to determine random strings. This is a famous quote by Claude Shannon. He talks about his conversation with Neumann, where he was worried about what to call this uncertainty, this probabilistic nature of bits in information, and how much information a bit conveys based on the probability of it being 0, 1. And he says when I discussed it with Neumann, he had a better idea than to call it uncertainty. He said, you should call it entropy for 2 reasons. In the first place, your uncertainty function has been used in statistical mechanics under that name of entropy, and so it already has a name. In the second place, and more importantly even, nobody exactly knows what entropy is. So if you have an argument with somebody about it, you'll have the upper hand, because they don't really understand entropy, because nobody does. So that was very insightful on the part of, so Shannon does give credit to Neumann. We just talked about Neumann half an hour ago, so there he comes up again. Any questions about any of this? And there's a very nice video, again, it's for extra credit, or actually, I think this is required, right? This is required. Claude Shannon, Father of Information. How many have seen this video already? Good. So it takes like a deeper dive into all of his contributions and the impact he had as a Claude Shannon Award. And some of the people that have won it are luminaries in their own right. And there's a diagram. This is the Information Theory Society of the IEEE. And look at that. This diagram comes straight out of his treatise on information theory, where he founded the entire field in 1949, actually. And this brings us to Stephen Kleen, but we'll continue this after a short break. Any other questions or comments? Or all right, so let's regroup in about 10 minutes and keep going.
Well, I know that you said it's actually language dependent, independent. If you're